And all the transistors we're going to look at, or transducers, excuse me, that we're going to look at are made out of semiconductors. They're all solid state. So originally, all our logic and everything was done with what we call relays and that kind of stuff. And the original adding machines were all done with gear ratios and all that other kind of stuff. Our original computers were basically mechanical. They were mechanical computers. So when we moved into vacuum tubes, these guys are no longer have no moving parts, right? So we started using the term solid state. And of course now we're using semiconductors and vacuum tubes are relegated to extremely high power applications. That's one of the problems we have with bipolar or semiconductors, is they can't handle a lot of power. And when we're talking about a lot of power, we're talking about up in the gigawatt range. So a transducer, what is a transducer? Have y'all heard this term before? It's another name for sensor. So, what does the sensor do? It takes some physical stimulus and converts it over to an electrical signal, which is exactly what your senses do. That's what your senses are doing. Your brain processes electrical pulses, right, coming up your neurons. And so you got the touch. Well, my brain don't know touch. My brain knows an electrical signal coming from those sensors, right? You understand, that converts it over. So a transducer is another name for a sensor, and they're used interchangeable. They mean exactly the same thing. So they convert some physical stimulus into what? Electrical signal, yeah. And once we got it as electrical, we have no problem. These are the ones that they cover in here. We're going to cover a few more. Something called a thermistor, a photoresistor, what most people call photocells. The technical term is a photoresistor or photoconductive cell. A photovoltaic cell, which most people refer to as a solar cell, a Hall effect sensor, and a piezoresistive device. And I'm going to cover some more in here that's not actually covered in the textbook. The first one we're going to look at is something called a varistor. But to understand, variac, first we need to understand the basics of a capacitor. And this will be even good for power supplies, but a capacitor consists of two plates separated by insulating material called a dielectric. And I think I put two of the leads together, right, and showed you how it coupled through to the oscilloscope, even though there was no mechanical connection or electrical connection. Capacitors are rated according to their ability to store a charge. The unit of capacitance is what we call farads. The more farads, the more charge we can hold. Of course, the more it costs, right? Everybody understand that? Pretty straightforward. So this is the basic makeup of a capacitor. We have dielectric, which is a name for an insulator, right? And then we have two blades, and we connect to the two plates. Now, what determines the amount of capacitance? Anybody remember? I think we talked about that a little bit in this class. Let me slide this back down so I can get to my markings. So I get to my pins. So what determines what we use for dielectric? We call it a dielectric constant. Yeah, the size of the plates. What else? How close the plates, the distance between the plates. And that's pretty much about it, right? You understand? So if I make the plates bigger, if I make the dielectric a certain material, if I get the plates closer together, the closer they are together, the more they're going to interact with each other, the more we can pass through them further apart. And of course, they're rated in at least two things. They're rated in farads. And what's the other thing? Volts. Because it's got a dielectric, and to get these capacitors, that dielectric is extremely thin to get these capacitors up to these sizes. And what that means is that it's very easy to get, if you got a too high a voltage, it's going to punch a hole through your dielectric, and then your capacitor is going to conduct current through it. It's going to. So is that the basics? Everybody okay on the basics of a capacitor? Really neat. I don't know who figured that out. Of course, we have capacitance. We call it stray capacitance. These are capacitors that are made that I didn't put there. They're just put there by, you know, we have a lot of problems with running power, how close we get them to other metals, and all that other kind of stuff. In a DC circuit, a capacitor is used primarily as a filter because of their ability to store a charge and block DC. They're also used as RC timing networks. In AC, capacitors are often used, offer an opposition current depending on the what? Frequency. As frequency goes up, the capacitor's opposition goes down, or vice versa. The opposition of a capacitor shows to the AC is called reactance and is represented by X sub C, but all opposition in a circuit is in ohms. So you can take every formula you learned, and if you learned it using ohms instead of R, all the formulas are the same. It's just now we have different oppositions in an AC circuit. This is the primary formula to calculate capacitance. This is 2 pi, so everybody understands that one. 2 pi. What's F? It's the frequency that the capacitor's in, and this is the size of the capacitor in farads. So the bigger the capacitor is, the less X sub C it has. The higher the frequency, the less X sub C it has. If I had a frequency of 0, what would X sub C be? God, I hope not. Take your calculator out and divide any number by 0. Yeah, any number divided by 0 is infinity. Because that's basically what people don't understand what division is. Division is multiple subtraction. When microprocessors first came out, the only two math processes they could do is they could add and they could subtract, and that was it. So what we had to do is figure out how to write a program to do division. We had to figure out a program to do roots and all this other kind of stuff. We had to figure that out. So what we do is we subtract by repetitive subtraction. So if I was going to take 25 and divide it by 5, this is what division is. We count how many times we can subtract that without generating a bar out there from no man's land, right? You understand? So this would go to 20, and then I subtract 5 again, this would be 15. Then I subtract 5 again, this would give me 10. Then I subtract 5 again, and this would give me 5. Then I subtract 5 again, and this would give me 0. And then I subtract 5 again, and now it generates a bar from infinity there. I count the number of times, 1, 2, 3, 4, 5, and that's what division is. Well, if I come up here and I say 1 minus 0, what am I going to get? Now, how many times can I subtract 0 without generating a bar? How often can I subtract 0 from a number without generating bars? Forever, right? Because what's 1 minus 1? I mean, 1 minus 0. Then I subtract 0 again, and that's what division is. So any number divided by 0 is infinity. And any number times 0 is 0. So that means it don't make any difference what 2 pi is. It don't make any difference what C is. If I got 0 down at the bottom, that's going to be 1 divided by 0, and that's infinity. So what that means, if I put pure DC on a capacitor, it's going to act like an open. So we say a capacitor blocks DC and blocks DC and passes AC. But as soon as I put a little wiggle on that DC, it's going to pass that, right? You understand? And that's why it gets rid of that ripple frequency. It blocks the DC, it keeps the DC, and just gets rid of that ripple frequency. So we did this. So what would be the reactance of a 0.001 microfarad capacitor in a circuit with 20 kilohertz? So we do all the math. So this is why one of the main reasons we have what we call the reciprocal key. So somewhere on your calculator you got 1 over x, or you got x to the minus 1. Anytime you raise a number to the minus 1, that's the same as taking the reciprocal number. So what you do on this is you do all this math, and then when you hit equal, and then you hit the reciprocal key on your calculator. But if anything under here goes up, then this right here is going to do what? Of course, this is not going to change. The 6.28 is what we call a constant. That's 2 pi. Are we okay? Frequency goes up, x sub c goes down, frequency goes down, x sub c goes up, capacitance goes up, and later on this will become important when we start looking at blocking DC and passing AC. Are we okay? We don't really know. So what we can do is a varictor diode is the amount of capacitance proportional to the size of the plates and inversely proportional to the distance between the plates. A reverse bias diode with its depletion region has all the makings of a capacitor. You understand that? So we got leads coming in the side, and then we got a place in there that's depleted of majority carriers. A reverse bias goes up, the capacitance goes up, and vice versa. So we can literally take this and we can adjust the size of the plates by what? By changing the reverse bias. And this is back in at the start, we say if reverse bias goes up, the depletion region gets bigger. If the reverse bias goes down, the depletion region gets smaller. It's just that if I get past when it extends out to the end, if I keep going, then the diode will break over, right? You understand that? So if we think about the leads of a diode as being the 2 plates, and we think about the depletion region, and by the way, those other guys are doped. What's the reason for doping semiconductors? What happens when you dope semiconductors? By themselves, without combining a P with an N or an N with a P. Y'all had that in your problem. Well, if we dope a semiconductor, its opposition goes down. It becomes more conductive. Because as soon as we dope it, we get more majority carriers, right? You understand that? So that means the P material will act like one plate, the N material will act like another plate, and then the depletion region would act like an insulator. What determines the size when we reverse bias it? Well, it determines by how much reverse voltage we put on there. So there we go. So there's our capacitor. But that capacitor is actually a variable capacitor. So anytime we put an arrow through a symbol, what does that mean like this? It means it's variable or adjustable. So it means if I change the size, if I make the depletion region bigger, capacitance would go down. If I make my depletion region smaller, capacitance would go up, right? A reverse bias diode that takes advantage of the capacitance of a diode is a depletion region. This is a varictor diode. We often move these in what we call tuned circuits. So what we got is how many, so what's media? Some of y'all should know that. What's media? Yeah, it's what information travels through. Okay, y'all understand that? So that's what information travels through. The information ridge. And then we have a term called multiplexing. Anybody ever heard of that term before? What's that? Yeah, when we let more than one information source share a common medium. We say signal, but and the perfect example is, of course, is air. How many signals do we have riding in the air right now? A lot. All your cell phones share the air. The car radios share the air, right? You understand? So we definitely use multiplexing. Well, what we do when we multiplex is we modulate the data or the information. Anybody know what modulate is? We probably use this term often, but modulate means we take the information we're trying to send and then we place it on a high frequency carrier. And then we send it out. And in that way, we can take all these signals and composite them together, and then we send them over the same medium. So that means your car, you see this on your radio in your car. When you select, we call it a tuner, but you ever looked on there on the right hand side, it says MH, it says this on the, when you say 93.7, you look over here, it says this somewhere. And what would that be? That would be megahertz. What you're doing is that's the frequency of the carrier. But what we need is we need to be able to tell our radio to tune in this carrier and do what? Like everybody else. So we have these things called tune circuits. So that's what you're doing. And we call that dial, what do we call that? We call it a tuner. So what you're doing is you tune your radio, you're setting up a tuned circuit that allows the carrier for a certain frequency to come through, and then what? Then we strip it off with filters. We strip off the carrier, and then we let the information come. So this would be one of those devices that is allows us to set up a tuned circuit. So we can make this guy here, we can tune this guy to allow a certain frequency to go through. Because you know, capacitors are what? They are sensitive to what? Frequency. Now, it takes more than this, but this would be one device that would be part of that. This is the symbol, by the way, of a varactor diode. So basically, it's a combination of a diode, and then this would be one of our symbols for a capacitor. And this would be a circuit. So notice what I'm doing. I'm putting AC in. I'm bringing it through a capacitor. What's the capacitor do? The capacitor is going to block the DC, let the AC pass through. Then I come over here. I have a little pot wired as a rheostat. This is going to change the DC voltage right there, which is going to change the reverse bias on the diode, which is going to change the what? The capacitance. So we let all these AC frequencies come through, right? You understand? Then I can come in here and tune this and only let one of them go through. Now there's more to it. We have to add more to it, but you can see how I got a device where this would be my what? This would be my tuner, and we're changing the reverse bias on the variac. And if I change the reverse bias, I change its capacitance. If I change its capacitance, I change its opposition to an AC frequency. Neat little circuit. We use these things. Used to use them a lot. There's a more precise circuit now we call a phase lock loop. Most of your radios use phase lock loops now. The problem with these guys is they drifted with frequency. Have you ever made any old radio restore those things? The channels constantly drift on those. So you're constantly on your what? Tuning them up. You had to do that on your TVs too. Everything we had a fine tuner on it. TVs had a fine tuner on it. Because what was happening is we was using these tuned circuits that were affected by what? By temperature. Semiconductors are affected by temperature. But that's a varactor. So what does a varactor do? Varies its capacitance with a reverse bias voltage. And you probably need to know the symbol for it. Symbols is the name of the game, right? If you pick one of these things up in your hand, it'll look like a diamond. This is another tuned circuit. But what this would be the actual way it would work. So to get a true tuned circuit, we combine a capacitor with an inductor. And what happens is these guys, so X sub C is equal to 1 over 2 pi FC. X sub L is equal to 2 pi FL. And these guys are just opposite of each other. So at a certain frequency, they're going to cancel each other out, which is really, really neat. You'll learn all about that in AC, but this would be an example of a tuned circuit. So I'd come in here and I'd put like plus 5 volts, and that would set up a tuned circuit. And it would only let one frequency come through. All the other ones, it would do what? It'd block them. All I do is just put a DC voltage into those things. It's really, really neat. Thermistor. We know that semiconductors vary their resistance with temperature. And we've talked about this several times. So if they vary their resistance with temperature, then what can we do? Well, we can use these things as temperature sensors. And these devices that sense temperature, they're referred to as thermistors. And they can be designed different ways. If it's got what we call an NTC, that's a negative temperature coefficient. That means the opposition goes down as the temperature goes up. If we got a PTC type, then that means these are positive temperature coefficients. So that means as the temperature goes up, their resistance goes up. Probably the most popular one is this guy right here, I think. Let's get one out. And we use these guys all over the place as temperature sensors. I guess I did. Okay. So I've got my meter right here, and this is and what I wanted to show y'all, this is an old digital thermostat before I upgraded mine. So and then I look at the back, and then right here, see the little white dot right there? You know what that is? That's the thermistor. So this guy right here is using a thermistor, and odds are, this one I like it because you can see the dang thing. Most of the time you'll see vents on the back of your digital thermostat, and there'll be a thermistor mounted up in there. So these guys are used all over the place. I didn't bring anything out to cut this with. So what we're going to do is we're going to hook this up to the meter. Normally they're off colored. These guys right here though, they look just like capacitors. So we'd have to probably be careful. So this is the thermistor, and what we'll do is so I won't have to hold it. I'm going to put it in the printed circuit board, and then we're going to get one of our meters. I've got alligator jumpers on. Okay. And we'll hook this up. I disconnected my other one. Okay. Hopefully I hooked up the right leads. I do that over. We're going to put it on ohms. So right now this has got, you'll see it. So right now it's got 1.1 K ohms. And all I'm doing is put my finger on it. You'll see what I'm doing? And what does it start instantly doing what? Dropping down. So Negative temperature coefficient means the resistance goes down as the temperature goes up. Okay, it's pretty much goes, huh? Resistance would go up as the temperature, it varies in the same direction. So notice as soon as I let it go, what did it do? Yeah, it started going up again. Covered up. So sometimes we get a soldering iron out here and really make it. You can get these that have different resistance ratings depending on what your application is. And these are nothing but semiconductors. So we use these guys here all the time to measure temperature, right? The only problem we have is that they're not linear. What does linear mean? Yeah, so a linear device would mean that its output varies with a straight line. This guy here has what we call an exponential curve. So its resistance actually varies with a curve, which like most semiconductors do, by the way. So you can see this example right here, the resistance would vary all the way from up to 190 degrees. It would be pretty close to 0 ohms. And as my temperature goes down, my opposition goes up, but it's not in a straight line. Now, it would look like this would be a problem. This can be corrected with computers. Computers have no problem with this. If they know the slope of the curve, then a computer can take a mathematical equation and calculate the exact temperature depending on what it gets out of the thing, right? Okay. But in a house, we don't have to do that, because in a house, what you have to understand, we're varying our temperature. What's the minimum temperature probably you'll get in your house? Yeah, the coldest in an average house. Probably around 60, maybe 60 something. We turn ours down. We like cold, so we love wintertime sleeping in there. Might get down to about 60 something degrees, so that'd be right here, and then it might get up to 80 something. Well, if you look at that, the curve is what? Pretty dang linear. So we have no problem in a house, because the temperature, the range span of a house is so small, we don't have to compensate for it, because the temperature, we almost get a linear curve there anyway, right? You understand that? But if I was going to measure this all the way between the range of the thermistor, then I would have to do something about it. And we have chips. We have chips, an LM 35 and a 34. These are integrated circuits, so they have circuits in them that compensate for the thermistor. And these guys are accurate. One of them is a Fahrenheit output, and one of them is a Celsius. And by the way, we can't sense resistance. Y'all understand that? So what would we do? Well, we'd take our thermistor. Normally we put it in a circle and put a T on it for a thermistor. Sometimes they'll put a little degree up there. Now, if I was to come up here and put a voltage source across this thing, what would I be changing? What would change with temperature? Not the volts. I mean, the battery's there. I mean, if it's a 12-volt battery, it'll be so what would change is the current. So the current would vary with temperature. Well, current is hard to get out and use as a sensor. So what we normally do is we'll take this guy, and then we'll put it in series with a fixed resistor. And this is the way the sensor would actually be. So now as temperature goes up, as temp goes up, its opposition would go down, and the voltage drop across that resistor would go up, right? You understand? So I could come over here and I could sense across that resistor right there. And now the voltage is going to vary with temperature. If temperature goes up, the output of the voltage would go up. If the temperature goes down, the voltage goes down. So normally, these transducers that vary their resistance, we usually put them in series with a resistor, with a fixed resistor. Does that make sense? Because it's hard to sense current. We can measure current, but it's hard to sense current, right? You understand that? We can sense voltages, so most of our transducers, and a lot of our transducers do vary their resistance. So if I had a temperature sensing probe, then odds are it's probably going to have a resistor in it. It's going to have a resistor in it. So you can buy temperature sensors for these meters right here. But those are usually thermocouples, by the way. Those are not semiconductors. Thermistors. So they're not linear. That's their biggest problem. But we work around that, right? Everybody okay? Photoresistors. We got, these guys are all over the place too. And they come in varying sizes depending on what we want to sense them for. I could pass the thermistors around, but they look like capacitors. Sorry, I need this one right in there. These are photodiodes. So what we do is we have a clear quartz or some type of clear epoxy or something on top of them, and then we expose the we expose the semiconductor directly to the light. If I can get my camera to focus. Now these guys here are, their resistance goes down when the light goes up. In the old days, before they figured these things out, and semiconductors were very popular, we'd have street lights, and all the street lights were on timers. So they would turn off at a certain time. You can still see old stores still do that. So in the summertime, you'll go by at 5 o'clock, it'll be bright as day, and their lights will be, because they're running off a wall, a time. We don't hardly do that. So all the street lights down through the Vesper Superhighway here, these are all on these little guys. Even the colleges are on these little photoresistors. So they're pointing up at the sun, and they got an electronic circuit in there that does what? Turns the lights on when it gets dark. Turns the lights off when it gets dark. I got robo lights around my front deck that's got a solar cell on there that charges the battery during the day, and at night they automatically come on. And what do they have in there? Well, yes and no. It actually uses the output of the solar cell, but it has the same principle. So let's come up here. I'm gonna hook this up, all right, and then I'm gonna move my meter over to this guy. Of course, it's showing me a resistance of the 500 and something ohms. Of course, it shot up there real fast, right? Let's just try to cover it up a little bit. So as the light goes down, what does it do? Resistance is doing what? Going up. If the light goes up, the resistance goes down. We use these a lot. We use them to measure light all the time. A lot of times on your camera, it'll have a photo cell on there. So it automatically adjusts your flash. So your flash determines if it needs to use the flash, if it don't need to use the flash. And they literally get the bounce off the flash to determine the length of the flash stays on too, which is pretty neat on most cameras. So these are called photoresistors. Most people refer to them as what? Photocells. All over the place. All these street lights up and down the Vesper Superhighway has photocells. I have motion detectors on my house that don't work during the day. They work at night because they have a photocell in there, right? You understand? My rope lights are look at the output of the solar cell. These come in all shapes and sizes. They come smaller, they come bigger, depending on how much current you're going to conduct through them. The ones that's in the street lights are pretty good size. They're about the size of probably a nickel. If y'all remember what nickels look like. We don't see much flat change anymore. I'm the only one in our family that carries money. My wife swipes everything. I've seen swipes for like 52 cents and that kind of stuff. That's true. So that's called a photoresistor. Everybody okay? Here's the symbol. Here's the international standard symbol. Normally we use these symbols right here. So notice they draw a symbol. If you see the arrows coming in, that means it's detecting light. Here's the same one with the circle around it, but it's got the, normally if we put a circle around it, it means it's solid state. Even though we shortcut on that a little while, like on our diodes and stuff like that, we usually don't put the circle around them. Originally they had circles around them. So there's our symbols. Are you okay there? Next guy we have, of course, is what we call, oops. It won't break, it's solid state. You slam it on the ground. That's not glass, that's just an epoxy coating. Yeah. So a photovoltaic cell creates a voltage. This is proportional, by the way, proportional to what? Light. So look at the symbol. It's got the symbol of a DC source, and then it's got the arrows pointing in. These are the ones we have. You can hook these things in. What do we hook sources for in series? When we hook sources in series, what does that do for us? Increases the voltage. When we hook sources in parallel, what does that do? Increases the current. You'll understand that. And you see that all the time, even in remotes. You know, you'll have batteries in series, batteries in parallel. So we can take these things, and so this would be a single cell. And then we got these from Gamaco. They're pretty neat. We got a big panel that I think Bell South donated to the college. And we had an LED on it, a little light emitting diode. And under fluorescent lights, you didn't have to put a resistor in series with it because it did put out enough energy. Nancy decided she was going to take that thing outside, so she took it outside. It got under the sun, and it popped that diode just like that. So she says that diode on the solar panel don't work anymore. But it's got a plus and a minus, and this guy's got two terminals up here, so we can do what? We can hook in series, or we can hook in parallel. These guys do not vary their resistance. So my thermistor, what would I have to do on that thing? Well, I'm going to have to put it in series with a resistor, right? You understand, to take a resistance and convert it into a voltage. We don't have to do that with these solar cells or these photovoltaic cells. So I'm going to come over here and I'm going to take my meter. I'm going to take it off of ohms, and I'm going to put it on DC volts. These guys here generate DC volts. And I'm going to hook it up. I'm not going to pay attention to plus and minus. My meter don't care. It'll come up. If I hooked it up backwards, it'll give me a minus voltage, but we understand that. Hook this one up there, hook this one up there, and we'll. So right now it's giving me 270 millivolts. I don't have enough room to get in front. Yeah, I do. Of course. Okay, now it's about a half a volt, and this is proportional. And we can use these things as light sensors. So this is what my my rope lights on my front deck does. It has a photovoltaic cell on it. And then it's got a little electronic circuit on there. It's got a little NiCad battery in there. A NiCad battery is a rechargeable battery, right? So what does it do during the day? Charges. And when the output drops down to a certain level, the little electronic circuit switches it over to the battery and turns the lights on. So it's using that as a two-fold thing right there. And these things are dropping down in prices. I think Harbor Freight sells a little 45 watt for not much. People, you can buy these things to charge your cell phone. It takes a long time, but you know, if you're out in the woods, you got two options. You can load a car battery with it and charge it with that, or you can just hook it up during the day and let it charge with these things. Pretty neat. So what these do is when the photons comes in and strikes it, these semiconductors absorb those energy from the photons and converts it into a difference in potential. And the one that they show here, they hook these things up in series and parallel and get the voltage they need. These big old panels are big. Are we okay? You see the symbol? You understand these things? Pretty neat. A Hall effect sensor. A Hall effect sensor is a solid state device that varies a voltage proportional to the strength of a magnetic field. Now we have two types, and I tried to look on a video. I saw a guy video on YouTube the other day. It was great, and I don't think I downloaded it. I'll look and see. But we have two types. We have what we call a latching Hall effect sensor. And then we have one that does this, that produces a voltage that is proportional to a magnetic field. So what we're showing down here in this little animated GIF down here is we have some magnets that's spinning around. And can you see what it's doing? Every time the magnet spins around, it pulses. By the way, these are all in your car. We use these to pick up for your usually your ABS system, your automatic brake system out there. So on your rotor, it's got a magnet, got a little Hall effect sensor sensing the speed of your actual rotors. Takes at least 2 wires. But these guys have to be powered up. So that means we got to have power on them. So we have this guy here powers up on 5 volts, and we have a common. So they either got 4 pins on them or they got 3. We can share a common signal, and then it's got a signal output. So I'll have to take one of these. I'll have to look this guy up and see if it's a latching. A latching type is pretty neat in that a latching type, once they're turned on, they'll stay on until you expose it to the opposite magnetic field. So that means if you turn it on with a north, you'd have to turn it off with a what? South. A linear type or an analog type, it's going to give you an output proportional to what magnetic field that it sees. So it means if we put a light out there and we got a magnet close, the light would get brighter, and as we moved away, the light would get dimmer. So the ones on your car, of course, are going to be those types because you couldn't reverse the field. But these are little old tiny things. And like I said, we'd have to look up the data sheet on this one. We might do that when we go on break next time. What? 3D printed magnets? Yeah. So what do you use? The string is magnetic or something?
No, they call it 3D printed, but it's not fully 3D printed. It's a little tricky enough to get it out.
Yeah. We have some really, really strong magnets now. I don't know, when we first got into stereo, I don't know if you ever saw the headphones, and I still like the big old headphones like this. Now, why we couldn't have the little earbuds is we didn't have a big enough magnet. And that's what you're doing. That's what you're doing. You got a diaphragm, and you have a magnetic field, an electromagnet, and it moves against a permanent magnet. I've got a speaker up here somewhere. Well, the problem is to get real good sound, you need a real strong permanent magnet. Well, now we got really strong permanent magnets. Some of them you have to be careful. They have them out there now that you don't want to get them between your hands. I mean, they have so much pull. I mean, they'd break your bones. And that's what's in our little old tiny headphones now. So we can get really good small headphones that have really good sound to them. I'll hook one of these up when we take a break. We'll fix that. So a Hall effect sensor, we can make it sense metal by putting a Hall effect sensor between a magnet, a permanent magnet, and then the metal we're trying to sense. Because magnetic field automatically concentrates to metals, right? You understand that? So these are different variations. Like I said, on most cars, it's in your ABS, your automatic braking system. You have it out on the rotors of your engine. A lot of times they'll put them on one of your gears inside your transmission to sense your speed. So if you got an attack gauge on your car, odds are it's got a Hall effect sensor in there, down inside there. These things are rugged. They don't mind being in grease and all kind of stuff, so we use these things all over. The manufacturing line over there has Hall effect sensors on them. So I think the Armatrol line has both Hall effect and reed switches, which those are not solid state. This is not in the book either, liquid crystal, but a lot of people don't understand the way LCD works. We used to say LCD, and now we say we have LEDs, but all flat screen TVs use it. We have two basic types. We have what we call plasma, which was very popular for a while. Plasma uses different gases that when you put electrical pulse through it, it's kind of like neon. They glow at different colors. What we do with liquid crystal is that we have send light up through it, and then what it does is it goes through the crystal, and if we put AC on it, can you see what the crystals do? They do what? They align. If we take the AC off the two crystal plates, then what happens is the crystal warps into 90 degrees. And what we do is we have a polarized lens on one side of the liquid crystal display. The light goes through, and then up here, this is offset by 90 degrees. So what happens if you got AC across there, this top lens does what? Blocks the light. If you take the AC off, then the light will follow the crystal and come out and come through the top. And then we put a lens out in front of it, and the lens is going to be a certain color. So we have what we call LEDs, but originally the monitors were backlit by fluorescent lights. So if you look like the one over on Dwayne's desk, you see his is real thick. The one beside it is real thick. Then you get over here to Chase, you see it's real thin. Well, the one that Dwayne's in front, it's a liquid crystal display, but it's backlit by fluorescence. If you look at Chase's, it's a liquid crystal display, but it's backlit by what? LEDs. So what we do on liquid crystal is we either open or close the shutter. That's what we do. And then we put a lens on the front of this, and what are the three primary colors? Yeah, red, green, and blue. So if you take this thing, don't turn on the light, and you put it up against your display and look at it, you'll be able to see the little liquid crystal. You can't see the crystals, but what you can do is you can see the lens. So when you look here, you should see three lenses, a red, green, and blue. If you look at white, you'll see them all. But if you move it around, if you get across black, you'll see that all of them's turned off. So we got a black background, right, to understand. And then we turn all of them on. They give us white, right? You understand? Turn some of them on or some of them off, and it affects what we get, any shade that we want. You got it? You see? You got to touch it.
Oh, I do.
You have an awful time trying to focus that. So what you're doing is you're not seeing the liquid crystal. What you're trying to do is, and they've made it very bad. Used to, the tube was pretty long. And so I don't know if y'all remember when flat screens first came out, you had what we call a viewable angle. Real bad viewable angle. So if you wanted to get a good shot, you had to look on them straight on because the tubes were so long. And we were shooting light through a tube, right? You understand that? If you go through a tube, then you're pointing the light, but they've got the tubes really, really short now. And you get a real good viewable angle on a lot of these TVs now. So that was the big advantage over a plasma over a liquid crystal, is a plasma had a real wide viewable angle, And it's still true, but there's a lot better. These are semiconductors, guys. Thank goodness for liquid crystal. Whoever figured this out. So that's what we got now. We got liquid crystal displays, you know. So how many still got old CRTs, the old cathode ray tubes? You still got one? Now you can still use it? Those things have a curved screen on them. Most of them have curved screens. The flat screens were real expensive because they actually electronically refocus the beam. Piezo-resistive. These are our pressure sensors. And I hadn't tried these out yet. We just got these. Well, there's not the mysteries. Dang it, Rich. So there's my Hall effect. There's the sensors. Like I said, when we take break, I'll hook this up because we're fixing to go to a lab so y'all can try to do y'all's Zener lab. Let me go find our piezo resistive. They've got this one here enclosed. This is one that's actually out. The actual pressure sensor. So this is a force sensor right here. Looks kind of like the photoresistor, but it's not. So what we have is so if you looked at the photoresistor, you'd see the two sides actually touch. On this one, you don't. So this is a force sensor. So hopefully when I come up here and hook this up and press on it, it should change. But like I said, we just got these in, so I'm praying if they work the way they're supposed to. But a pressure sensor senses pressure, right? So that's not exactly what this is, but it's close. So we have a photoresistive element, and so what does that mean? I mean, piezo. Anybody know what piezo means? Yeah, senses pressure. So we have piezo-resistive, we have piezoelectric, we have let's see what Wikipedia says. As I get my fingers on the right key. Oh, it's PIE. I'm sorry, PIE, right? PIE. Yeah. That's piezoelectric. I don't see just piezo. Let's see what this says. The ability to certain material to generate a this is piezoelectric. You run these all piezoelectric. Y'all know where y'all run it. Piezo is predominant right now in cigarette lighters. No, it's regular old butane or propane or whatever. You know, you got the little thing. Used to, you had a flint, had a little wheel. You spun around, hit a flint, and shot a spark out there. You don't have any money. You got a little old button that you push, and you hear a snap. And what's it doing is popping up against a piezoelectric crystal. That's what you're doing. You're popping that piezoelectric crystal, and what does it do? It generates a voltage and causes it to do arc. For it to light as well? Yeah, I was going to say they don't work the same way. So I don't see piezo. So piezo means it does something with pressure. So piezoelectric generates an electrical pulse with pressure, right? Piezo resistive would change its resistance with pressure, right? So the only definitions I see is piezo electrical polarity produces a, let's see, yeah, so piezo means it produces something resulting from pressure. You understand that? So piezo resistive would mean what? Changes resistance with pressure. So this would be a piezo resistive pressure sensor. So this guy right here would change its resistance with pressure. And these are some solid state pressure sensors. A lot of your pressure sensors are solid state. We have different types of pressure sensors that when you get into, so this is actually a pressure switch. I got one somewhere that came off my compressor. Came off a compressor. And then this is a pretty good place to stop. So we're going to cover some stuff in this book. So transducers, we have what we call photoelectric transducers. So what we're going to do is we're going to go ahead and cover LEDs. Right? Y'all know what LED is? Right. And then once we do that, we can come in and look at what determines them, and then we can look at some photoelectric sensors. So they use LEDs. And then we get into the actual photo sensors. But I think they have a whole chapter. So we have a chapter on transducers, but then they stop with these transducers right here. So what we're doing is we're also looking back. We're going to do all the transducers at one time. So where's the other chapter? Where's the ones on what chapter is photoelectric? It's way back there. I don't know why they didn't do them all at the same time. This guy here actually covers some fiber optics too, which we're not going to get into. So what chapter is photoelectric? Photonics is chapter 15. So some of the stuff we're going to look at right here in our next class is we're going to look at some stuff. So we're going to cover LEDs so we all understand photoelectric sensors. And then we'll go over there to the manufacturing line and see if y'all can find all these things. Are we okay? All right, guys, let's go to lab.